In today's video, we are going to go one step further than what we did yesterday, where we graphed parametric functions. And today we're going to talk about the calculus of parametric functions, or at least the differential calculus. We're going to be talking about derivatives again. What you have to understand about parametric functions, which, if you recall, are functions that look like this, where the x value of any point on the curve and the y value are both defined by t, meaning we've got an x variable, a y variable, and a t variable, 3 different variables. That means that the derivatives of those 3 variables, the rates of change of those 3 variables, all depend on each other, which means we're going to have a few different rates of change to talk about. The first one, there's no particular order here, but the first one is dx dt. That's the rate of change of the x value, or the horizontal rate of change, as time goes by. How much is the coordinate moving to the left or to the right? Well, if we talk about how much the coordinate is moving left or right at any given moment in time, we can talk about how quickly or how much the coordinate is moving up and down at any rate in time. That's the vertical rate of change. dy dt is the vertical rate of change. And there is a third derivative that we care about sometimes also, which is the one we're used to, dy dx, which I know it's what we're used to, but it's actually the weirdest of the 3 in this case. Because in this case, x changes as t changes, and y changes as t changes. So it's weird to talk about the rate of change of y in respect to x. It's a weird idea. It doesn't really make that much sense physically, but it does make sense graphically. It means the same thing that we saw before. It is the slope of the line tangent. To any coordinate on the curve. So those are our 3 derivatives. We'll look at an example, and if we have time, we'll come back to those vectors at the bottom there. So here is a parametric function. X of t is cosine of t minus 1, and y of t is t squared over 2 minus 2t. Take a second to type that into a Desmos screen. I've got it up here. I want you to notice, unfortunately, I have not figured out a way to use x of t and y of t as names of functions. Desmos doesn't seem to like me to use x and y as dependent variables. It's not a big deal, we'll just use different names. And then if I want to graph the coordinate x comma y, I'll just type it in as f of t comma g of t, because that's the names I gave for my x value and my y value, and I'm going to have it graph from 0 to 2 pi. And at the same time, I also really like being able to see what's happening at any moment in time. The problem with this graph is this shows me the path that the coordinate makes as time goes by. It doesn't really show me what's happening. For all I know, the graph starts up here and moves down along this way. Or maybe it started here and went this way and then came back. I don't know. So what I'm going to do is graph the same x comma y using my functions f and g, except this time I'm going to use a slider so that way I can look at one point at a time instead of calling it f of t, where it'll show me all of the points when t is between 0 and 2 pi. If I use a and make it a slider, it can show me only one number at a time. So I'm going to also make my slider go from 0 to 2 pi. Let me just make it so that it only goes once. And you can see that this point, when t is 0, the coordinate here is 0.540, which means the cosine of -1 is 0.54, and 0 squared over 2 minus 0 is 0. That's why that's the coordinate. And as time goes by, the coordinate will move that way, and then down, and then back up, and then it'll keep going like that. Now, if I would have let time get bigger than 2 pi, this y value would have just kept going up. If this is a quadratic, it's on its way up, it'll just go up and up and up and up and up. The x value will keep going back and forth, but the y value will just be shooting off the screen. So I stopped it at 2 pi. So we've looked at our graph. We have a sketch of the curve. If I want, I can put a quick sketch on here. The graph started here, it went like that, down, like, it's a rough sketch, but that's pretty much what it looked like. I want to find any point where dx dt would equal 0. Well, what does it mean when dx dt equals 0? The horizontal rate of change is 0. It means for one split second, for one instant, the graph is neither moving to the left or to the right. Look and see where that happens. I'm going to slow this down a lot so we can talk about it as it happens. The graph is moving to the right. Now it's to the left. Well, if it was moving to the right and now it's moving to the left, that means at some spot in here it wasn't moving to the right anymore, but it also hadn't started moving to the left yet. Well, that spot is right at that spot where there's a vertical tangent. So dx dt equals 0 means there is a vertical tangent. Or I should say, could be there's a vertical tangent. Where there is a vertical tangent, dx dt must equal 0, but it's not necessarily the other way around. So if we look, there's one there. There's another one later here, where the graph, it was moving off to the left, and just for a split second, it stops moving to the left, and before it moves to the right. So it's dx dt was 0 right in there also. So we'll have dx dt will equal 0 here, and also here-ish, those 2 points. Well, I want to find out when and where do those points occur. In order to do that, I need to know what I mean when I say when and where. So when you're asked in a parametric function, if you're asked when something happens, that means you're being asked for a t-value. And if you're asked where something happens, that means you want both the x and the y. You want the coordinate. So make sure you understand those two questions. In order to do that, we want to find out where dx dt equals 0. Well, I can find dx dt, because dx dt is just the derivative of that. The change in x in respect to time would be the negative sine of t minus 1. Had there been a derivative to my inside function other than 1, I'd make sure to include it, but I don't have to worry about that. And so if I want to know where does dx dt equal 0, so negative sine of t minus 1 equals 0, well, when does sine equals 0? I can ignore the negative, or multiply both sides by negative 1 to get rid of it. When does sine equal 0? Well, we know sine equals 0 at 0 and at pi. So that means the angle could be 0, or the angle could be pi. So the two values for t are 1 or pi plus 1. Pi plus 1 is this 4.14. 3.14 plus 1. I can't get it to exactly 4.14. Well, I can type it in. And you can see that's right at that vertical tangent there. The other one was at 1, which is the t value back here at the other vertical tangent. So we've already answered the question, when does it occur? If I want to know where that happens, I need to find the two coordinates. I need to find x of 1, comma y of 1, which is the cosine. X of 1 would be the cosine of 1 minus 1, the cosine of 0, which is 0. Sorry, the cosine of 0 is 1. And then the y value would be 1 squared over 2 minus 2, or a half minus 2, which is negative 1.5. And if I look at my coordinates, if I wanted to, I can add a label to that point and see that is the coordinate right there, 1, negative 1.5. The other one, t is equal to pi plus 1, so I want to find the cosine of pi plus 1 minus 1, or the cosine of pi, which is negative 1. And pi plus 1 squared over 2 minus 2 times pi plus 1, like that's an annoying number. I'll just write it in that way. I wouldn't be expecting you to do those calculations on your own, but if you move it over, it's right here. If I actually wanted to, I could type in exactly pi plus 1 here, and it'll do the math for me. So that's the second coordinate, where it happens. Okay. Moving along, we'll also find points where dy dt equals 0. Well, we can start by finding out what dy dt is. Dy dt is the derivative of y of t in respect to t, which is, bring down the 2, so that's 2t over 2 minus 2. And so, of course, that would equal 0 when t equals 2. So when and where do those 2 points occur? After 2 seconds, I'm just going to say that t is measured in seconds right now. And the coordinate will be cosine of 2 minus 1 is the x value, and 2 squared over 2 minus 2 times 2 is 2 minus 4, which is negative 2. And so the coordinate where dy dx, when t is 2, you can see my coordinates there are cosine of 1, comma, negative 2. And we can see that this makes sense, that this is where dy dt is equal to 0, because we have that is a spot where there's a horizontal tangent. The function has stopped going down for an instant and is about to start going up again. Now the trickier part is dy dx. dy dx means the same thing it always has, the slope of the tangent line. It's just not really rate of change, so I wouldn't use that term anymore. But the way I'm going to find dy dx is by finding dy dt and dividing it by dx dt. Well, I've already found dy dt. It was t minus 2. And I've already found dx dt. It was negative sine of t minus 1. And so that's my dy dt. If I want to know, sorry, that's my dy dx. So that is the slope of the tangent line at any given value for t. So if I want to know what is dy dx after 1 second, I would simply plug a 1 in there. 1 minus 2 is negative 1. And negative times the sine, oh, that was a bad example, times the sine of 0, well, this does not exist. That's, I should say it's undefined. Sorry, that was a bad example to pick because I forgot that when t equals 1, the point is right there, the tangent is completely vertical, which means its slope doesn't exist. If I were to pick any other number, like let's say 3.5, if I were to try to plug a 3.5 into the equation for dy dt, which was, I'm going to give that a name, let's just call it h of x, just so I can use it, was x minus 2 over negative sine of x minus 1. I could have used t instead of x here. I don't really want to look at that. But I can find out the derivative at 3.5 is negative 2.5. And if you notice, that makes a lot of sense here because this graph looks like it has a slope of about negative 2.5. I know it doesn't look like that right now, but that's because the graph wasn't a perfect square. Now that it's a perfect square, you can see that it does look like a slope of negative 2.5. One last small thing to think about, just a couple of bits of terminology here. This does not change what we do at all, but there are specific names to a little bit of what we've done before. We get into something called vectors. A vector is simply an ordered directional pair, or an ordered pair grouping of numbers. When we're talking about parametric functions, the position vector is just the x position and the y position. The same thing as the coordinate. Usually when we call it a vector, we use a slightly different symbol. Instead of parentheses, we use that little caret thing. It doesn't change anything. The velocity vector would be dx dt, or if you want, you can call it x prime of t, y prime of t. We call that the velocity vector. These two numbers are the direction, the horizontal rate of change, and the vertical rate of change. So what do you think we might call x double prime of t, y double prime of t? Well, if it's the derivatives of the two velocities, or the derivative of dx dt and dy dt, so the second derivatives, it makes sense to call it the acceleration vector. So a lot of times you're asked to find either the position vector or the velocity vector or the acceleration vector of a parametric function. And that's all it's asking you to do. It makes it sound more complicated than it really is. And by the way, if you want to, you can of course use Desmos to find, let's say, if we wanted the velocity vector after 2 seconds, you could just type in f prime of 2, comma, g prime of 2. And what it does, it's a little bit weird, is it puts it on as like a spot on the graph. But if you label it, that's the velocity vector. If you want the acceleration vector, you of course could say f double prime of 2, comma, g double prime of 2. And again, this dot, the placement of the dots doesn't mean anything to us. What matters to us are the two numbers there.